Okay, we're going to go over just a little bit more theory, then we should be completely done with our introductory stats lesson, okay? Now, you'll notice that in the previous examples, our degrees of freedom, which was n sub x minus 1 plus n sub y minus 1, that equals our degrees of freedom. That's related to, again, our sample size of each treatment. N sub x is the sample size of treatment x, n sub y is the sample size of treatment y. Why does that matter? Well, you can tell by looking at your t-distribution table, which I'll come back to in a second, but basically the greater your sample sizes are of each treatment, the more likely you are to detect a difference between treatments X and treatment Y, if one does in fact exist, right? So if there is a true non-random difference between treatments X and treatment Y, no matter how small, if you have a really, really large sample size, you're more likely to find it, okay? And the reason that is because if you have, let's say, an entire population, let's say, just take into account the human population, right? In our example, we were measuring the difference between a group full of men and women, right? And of course, population, which is represented by the circle, is usually denoted in statistics by a capital N, right? And sample size, meanwhile, represented by this little circle, is usually denoted by a lowercase n, okay? And so basically, assuming non-random sampling, assuming that you're sampling or surveying people from a population in a non-random, non-biased, objective fashion, the larger your sample size is, again, in theory, the more representative it should be of the entire population, right? In most instances of study, you'll never be able to sample an entire population of whatever it is you're studying, but the larger your sample size, especially of both treatments, the more likely you are to find a difference between your two treatments if one is in fact real, okay? And that is referred to as, if you're increasing the sample size, you're basically avoiding a type 2 error, right? A type 2 error is essentially a false negative, right? You're probably more familiar with examples of this in, say, medicine, right? So let's, for instance, say you go to an oncologist, he scans a tumor, or he scans a mole or some tumor he finds, and he says, okay, it's not malignant, you're fine. And then 2 weeks later, you keel over and die. That's the danger of a false negative, especially within a medical context, all right? Another way of defining a type 2 error is failing to reject H null when in fact you should reject it. So basically that goes back to the larger sample size, right? Because if there is indeed a true difference between treatments X and Y, the larger the sample size, the more representative your samples are of your greater population, the more likely you are to find a true non-random difference between your treatments should one exist, and that way you're decreasing the likelihood of a false negative. And this is further represented mathematically on the t-distribution chart. You note that all these critical values, no matter what probability column we're talking about, the further you go down on the degrees of freedom column, which is, again, degrees of freedom is a proxy for overall sample size, the smaller these critical values become. And that means the less the less big your t-value has to be in order to pass these critical values. So again, please note just that the one takeaway from this is that the more degrees of freedom you have, the larger sample size you have, the smaller the critical value is that your t-value has to surpass, the more likely that your results will be statistically significant. Now, the other type of error we're worried about is just the opposite, and that's called a type 1 error, which is the inverse, like I said, it's the inverse of a type 2 error, and that's called a false positive, right? It depends on what context, what type of research you're actually conducting, which one is considered quote-unquote worse than the other or more dangerous than the other. In a medical context or biomedical context, type 2 errors are generally scarier, right? That was the cancer example I listed. An example of a type 1 error in the oncology example could be you go to an oncologist, he scans a tumor, he says it's malignant, he says, oh my God, we got to operate. And maybe weeks later he does another biopsy of that same tumor he removed, and it turns out it's actually not malignant. I don't know if they can actually do that once they remove it from your body, but point being, a type 1 error, a false positive, is scary, but there doesn't tend to be as much damage within a medical context. So it's basically type 1 errors are rejecting H null when you shouldn't. Okay, and I think this is one generally that's easier to understand. It's basically you're claiming that you found something interesting when in fact you found nothing interesting at all. And the easiest way to avoid a type 1 error is just to go back to the null distribution chart, is just change your cutoff value from 0.05, make it instead 0.025 or 0.01 or 0.001, whatever. Make your cutoff for statistical significance more extreme. Okay. Now again, you'll note the danger of doing that. The more stringent your cutoff level for statistical significance, which again is just arbitrary. In this class, we're just choosing 0.05 because that's the one most commonly used in the life sciences and most scientific research, for example. The danger of decreasing your p-value cutoff point, which is also known as alpha, p-value cutoff for statistical significance. The danger of doing that is that you therefore make a type 2 error more likely, right? Because if you set your alpha value at 0.00001, you have to get a huge t-value, unless of course you have a huge sample size, in order to actually detect a true trend between x and y, again, assuming one exists. So therefore, the best way to avoid both type 1 and type 2 errors is to, for type 1, decrease alpha value, which equals your p-value cutoff. And for type 2 errors, you just increase n sub x and n sub y. Basically increase all the sample sizes of your treatments. And that's it, we're done.